My name is Tejas Naik and I will be giving a presentation on fast Fourier transform. So let's start with the discrete Fourier transform. Discrete Fourier transform is a mathematical operation which can be represented in the form of a matrix, and the fast Fourier transform is a computationally effective way of computing this discrete Fourier transform. So if we are given a continuous analytic function, for the analysis of it we calculate the continuous time Fourier transform. But many times what we have at hand is experimental data which is obtained from some measurement, and those data are finite sample points. Okay, so for the analysis of that we calculate the discrete Fourier transform, the formula for which is quite similar to what we have in the continuous time Fourier transform. Okay, so in the matrix form it can be represented as this matrix. Okay, so if we have a data of n points and we want to compute a discrete Fourier transform, so we'll multiply this matrix and this would be the discrete Fourier transform which we obtain. So these coefficients here represent that how much of a certain frequency is present in the actual signal. So what we assume is that if these are n points, we assume that there is an underlying function, continuous function, which passes through all these points. So these coefficients here, the computed by the discrete Fourier transform, shows us that how much of the certain frequency component is present in the actual signal. So A0 would correspond to the frequency 0, that is just the DC value. Then A1 will correspond to frequency 1, all going up to n minus 1, which would correspond to a frequency of n minus 1, which means that if there are n points, the function oscillates between every point. So if you want to compute this, the computational complexity scales as order n square. By computational complexity I mean the number of multiplication or the addition operations. So if you see here, there are n cross n columns and rows, and this is a n by 1 vector. So there are n square operations in here. So can we do any better? So we can think of some other problem and then come back to it later. So if I have two polynomials ax and bx of degree n minus 1 both, I can represent it in coefficient form, where I just represent the coefficients of polynomial a and polynomial b. So it just means that a0 plus a1x plus a2x square plus dot dot a to the power n minus 1 x to the power n minus 1. Similarly for b. And now what I want to compute is a polynomial c, which is the product of these two polynomials a and b. So if a and b have degree n minus 1, c would be having a degree 2n minus 2, right? So that would be 2n minus 1 coefficients which we need to compute. As you see that the index of these coefficients is equal to the power of the x which is multiplied. So c0 corresponds to x to the power 0 coefficient, c1 corresponds to x to the power 1 coefficient. So what we just need is that for a coefficient with index ci, the sum of the product, so a and b, this sum should be equal to 1, and it should be sum of all those such multiplications, right? If you look closely, this is nothing but the convolution of the two vectors a and b, right? If we were to represent a and b, so if you look closely, here I have said that there are n coefficients of a and n coefficients of b, but for computation of c we require 2n minus 1 coefficient. So we need to pad a and b with zeros to 2n minus 1 coefficients. Okay, so this is nothing but the convolution operation. Okay, and the complexity required for the multiplication of two polynomials a and b is order n square, because each coefficient is to be multiplied by n coefficients here, and there are n such coefficients, so order n square multiplication. This is the coefficient form. What if we consider the point value form? So A and B are bounded by degree n minus 1, right? So they are degree n minus 1 polynomial, and C is a degree 2n minus 2 polynomial. So we would be requiring, so we know that by the fundamental theorem of algebra, if there are n points, we can pass a unique n minus 1 degree polynomial passing through all of these points, right? So for the specification of the polynomial C, we would be requiring 2n minus 1 points. Okay, so let's define those points to be m. Okay, now in point value form, it's just a simple multiplication of A and B, point to point multiplication. So we need to calculate A and B till n points, and for C, it would be just the product of, it would be just the point to point product of all the points which we have sampled. If you look closely, this is just a linear time because there are linear number of multiplications in M. So in this representation, we do have an advantage in the computation of multiplication over the coefficient representation. So what if we try to convert the coefficient multiplication coefficient form into the point value form? So what we need to do is evaluate the polynomials A and B at m points, because we want to calculate these points. So at m points, and then we can do a point-wise multiplication in this point value form because it is easier in here, because it will just amount to order n time, linear time. And once we get these points, we can interpolate it by some numerical methods to obtain the coefficient of polynomial C. So for evaluation, what we can form is a van der Waals matrix of m values. Okay, so for here evaluation we require m points. Okay, so we would be forming a matrix of m such x values, and we can compute it. But if you see, this would also take order n square time, and the best known interpolation methods such as the Lagrange polynomial interpolation also takes order n square time. So somehow, if we find a better way to swing between these two representations, then our job is done. So that is done by the divide and conquer method. So as we saw, our goal was to compute the polynomial A and B for the points x, okay, for the set, for some set x, where the dimension of x would be m, the number of points which we have to calculate. Okay, so what we do is we divide the vector of coefficients A into two equal parts, the even entries and the odd entries. So A even would be a coefficient vector with all the even entries A0, A2, A4 till n, and A odd will correspond to all the odd entries. Okay, so like we wrote for the C equation for the polynomials, we can write it for A even and A odd in the polynomial form here. So if we want to write AX in terms of A even and A odd, so we can represent it in this form. So we know that the index of the coefficient will correspond to the power of x in the A polynomial, right? So if you want to somehow incorporate A even to display AX, we would have to square AX, we would have to square x, so we would have to input x square. Okay, so this would correspond to all the even powers of x, and for the odd power we can square it, but there is one remaining, so we can multiply x outside. So we can represent A as a divided sum of two different coefficients, so the even coefficients and the odd coefficients. Okay, now if we assume that let t be the time taken for the evaluation of the A polynomial, which has a vector size m, right? So there are m coefficients in the A polynomial, and we have to compute it for the x for a set x with dimension this. So we divide it in two sub problems, A even and A odd. Now for A even, we have only m by 2 coefficients, okay, and we need to compute it for all the points which we stated earlier, and there is some linear overhead. So order m corresponds to the time which we need for sorting out these two a1 and a odd coefficients, and order x would correspond to this multiplication operation which we are doing. So this is a recursion problem, and it is in two variables. So we need to solve using a binary tree, and if you solve it, it still comes out to be order m square. So even after doing this, we are not getting any improvement. So what we really need is, along with decreasing m, so we saw that when we divide a into 2 even and odd, the vector size reduces to half, but we are still computing it at all the points, right? So if the size of x would reduce to half, then it would just be a recursion in one variable, and that would solve to order m log m. Okay, so how could we achieve that? So what would be the set of number x which when squared, right, which when we divide, and so for inputting in a1 and a odd, we are squaring the set, so which when squared reduces the size to half. So that would be the square root. So if we square the square roots, we would get the same number, right? So squaring the square roots reduces the size of the set by half. So I'll explain this by the next example. So if we take the square roots of unity, let's consider, for example, the x equal to 8 case. So we are considering 8 root of unity. We are having here 8 numbers. So if we square this, 1 square would be 1, omega square would be omega square, omega square square would be omega to the power 4, omega cube square would be omega to the power 6, omega to the power 4 square would be omega to the power 8. But we know that from the properties of nth root of unity, omega to the power n is equal to 1. So this is again 1, right? So basically we can see that omega to the power k and omega to the power k plus n by 2, right, after the n by 2, those have the same square. So when we square it, those would actually give the same numbers, and hence would collapse the size of the set to half. So for the n equal to 8 case, if we have 8 coefficients, we divide it into even and odd sets. Here we have all the even coefficients, all the odd coefficients. Then we can consider this as again a problem, and as our set A, or as our polynomial A, and we can again divide it into even and the odd. So here even would be a0 and a4, odd would be a2 and a6, right? Then we can do it recursively till we obtain only single coefficients, right? At this point we have to just calculate it at only one point, and the computation is very easy, because at this point the evaluation of the polynomial is just the coefficient itself, right? So I've written a MATLAB code for it. If we are given a polynomial a as a vector, right, and m is the size of the vector and w is the mth root of unity. So if m equal to 1, as I said, it would be just the evaluation would be just the coefficient itself, okay, and we divide it in even and odd, okay. In MATLAB indexing starts from 1, but our convention assumes from 0, right? So from 1 to m would be the even in steps of 2, and from 2 to m in steps of 2 would be the odd entries. Then we compute it for the even and odd, we evaluate the function. Now we have this property, as we saw earlier, that the omega to the power k and omega to the power k plus n by 2 have the same square, right? So omega to the power I and omega, so the ith entry and I plus n by 2 entry would be multiplied by x and minus x, okay, because both these have the same square, so one would be the negative of the other, okay. So we are half done till now. We have obtained a efficient method of going from the coefficient form to the point value form. Now we can perform a point-wise multiplication in linear time. Now what we need is to go from point value form again to the coefficient form, right? So it can be done by the inverse Fourier transform. We saw that this is the DFT matrix. So the inverse of it is just obtained by replacing omega by omega to the power minus 1 and a multiplication factor of 1 by n. Now the striking property that omega to the power minus 1 can be written as omega to the power n minus k. Now so it can be written as omega to the power n minus 1, it can be written as omega to the power n minus 2, and this can be written as omega to the power 1. So these are still the roots of unity, right? We can still use the collapsing property of it to bifurcate into even and odd entries. So we can still use the fast Fourier transform algorithm for the computation of inverse. What we just need to do is we need to replace here w by w inverse, right? And we need to add a multiply by a factor 1 by n. Okay. So our final algorithm would correspond to this. So when we are given a and b in the coefficient form, we need to calculate the fast Fourier transform, which will convert into the point value form, which would take order m log m. See, if you see, this is nearly linear because log m would be a very small value as compared to m. So as m grows bigger and bigger, this method would actually be very helpful. Then we calculate the product in the point value form, which is just the dot product of all the coefficients of all the values which we have formed from this, the point values. This would be just linear in time, and then we can calculate the inverse fast Fourier transform, which also sums to m log m time. Okay, so if we see that this is something which we would require as signals and systems, because given an LTI system, a linear time invariant system, and if we have an input, we want to calculate an output up to it. So what we do is we convolute the input with the impulse response of it, right? But we saw that the convolution operation is computationally not good. Okay, so it's computationally costly. So what we can do is we can apply fast Fourier transform on both the input signal and the impulse response and convert it into the frequency domain. So in the frequency domain, it's just the dot product of these two. So the input signal and the impulse response, and then we can again apply an inverse Fourier transform to get back the output signal in the time domain, right? So this is one of the application. The next application I will be talking about is denoising the data. So suppose assume that if I have been given a signal, the black signal, okay, this is the actual signal, but due to the environmental noise, it has been attenuated and I get the blue signal. Okay, now I want to mitigate this noise and get the actual signal back, right? So we can apply a Fourier transform here, because we know that the Fourier transform shows the weight of the frequency components which are present in it, right? So I assume some clean signal with frequency 50 and 120, and then I added some random noise to it. So this is the actual signal, this is the noisy signal. Then we apply a fast Fourier transform to obtain the Fourier coefficients FAT. Now I need some measure of the magnitude of the frequency component present. So what I do is I calculate the power spectrum. So power spectrum is nothing but the magnitude of the f hat which is present, the frequency coefficient. So we just multiply it by the conjugate. So that would give how much of that coefficient or how much of that frequency coefficient component is present in the actual signal. Okay. So if we plot it, we see that we obtain peaks at 50 and 120. So what we would actually expect, because these are the actual frequencies which we have. And what we can do is we can set some thresholds. So power which have so the frequencies which have power above 100, we can only consider those, and we can kill off the frequency, the power which the frequencies which have power below 100. Okay. So we are only considering the power spectrum whose value is greater than 100, and then they can apply a inverse Fourier transform to the frequency coefficients, and then you see we obtain the actual signal mitigating the noise, right? So this is a very useful application of the fast Fourier transform. Last but not least, I will talk about other applications of fast Fourier transform. So it is used in digital signal analysis because it converts to frequency domain with very fast speed. Then it's used for denoising of data, as we saw earlier. It's used for computing the derivatives, which are used for solving the partial differential equations. It's also used for audio and image compression. So the FFT algorithm is at the heart of all these applications.